So we'll look at a little practice question in preparation for our quiz tomorrow on multi-force problems. It says, Adam pulls a big bag of Halloween candy, 7.5 kilograms. So it is a pretty big bag of Halloween candy, almost 20 pounds of candy, to the right with a force of 20 newtons. Sydney pulls it to the right with a force of 25 newtons. And Rachel pulls it to the left with a force of 30 newtons. What's the acceleration of the bag of Halloween candy? First thing we do is, of course, draw a free body diagram. What forces do we know are acting on this bag of candy? That is, if it's sitting on the ground as it's being pulled by these three people.
Force of gravity and normal.
Right, we have gravity and the normal force, but we don't worry too much about those because we know those two forces are going to, right, they balance each other out, they cancel each other out, so they're gone. When we can do that, so much the better because it makes our analysis way easier, especially if those forces are in a different dimension like they are in this case, the y component. All right, what else we got here? Adam pulls it to the right with 20 newtons. So let's make the force of Adam to the right 20 newtons. We're going to call that Fa. Sydney is pulling it to the right with a force of 25 newtons. That's going to be slightly bigger than the force of Adam. Call that Fs for the force of Sydney, 25 newtons. And then we've got Rachel pulling it with 30 newtons to the left, which we should make longer than both of those. We'll call that Fr. Now, if you wanted to make those, F1, F2, F3, that would be fine. It doesn't make any difference. If there was friction added into this, I didn't put that in there, but if there was, which way would friction act? Say a force of friction of 2 newtons, which way would it act? It would act to the left? How do you know? Good. In the absence of friction, it would move to the right. That means if we add friction, the friction is going to act to the left to oppose that motion. So if there was any, it would go to the left. All right, next step is to, somebody told me a little while ago, we add the forces up. It was Kyle, right? Yeah, we add the forces up. So we say F net is equal to the sum of the forces. I'm saying Fr plus Fa plus Fs. You might have said F1 plus F2 plus F3, whatever. Now our next step, if we were looking for the net force here, then we just sub in our numbers and solve for the net force. But we're not. We're looking for acceleration. So there's something else we got to do before we sub our numbers in. What's that? Adam, what are we going to do here before we sub our numbers in? F net is also what?
Oh, mass acceleration.
Good. Mass times acceleration. Now, F is equal to m times a, whether we've got one force or 20 forces acting. If we have one force, we just set F is equal to m times a and do our thing. If we have 20 forces, then we set F is equal to m times a and then set that equal to F1 plus F2 plus F3, however many forces we have. It's always ma, though. Fr plus Fa plus Fg. M is 7.5 kilograms. A is what we're looking for. Fr is 30 newtons. Fa is 20 newtons. And Fs is 25 newtons. Is that right? Yeah, Jordan, what's wrong? Good. 30 needs a negative because it's going to the left. If we had had friction, then that friction would have needed a negative as well because it was also going to be to the left. So we add these up now. 20 plus 25 is 45. Subtract 30 is 15. We got 15 on the right side divided by 7.5. Gives me an acceleration of 2.0 meters per second squared. How many people got that? If you got that, you should probably be fine for tomorrow's quiz. The only thing that I could see adding, and I haven't made up the quiz yet, but the only thing that I could see adding beyond what we did here was some friction. And friction, you just got to remember, is always opposing the motion. So if it's going to move to the right in the absence of friction, then we're going to make it, we're going to make the friction to the left. If it's going to go to the left in the absence of friction, then the friction is going to go to the right. All right? All right, yesterday we spent some time talking about Newton's third law. And I think somebody stated Newton's third law to me the way that you learned it in grade 6 or grade 5 or whenever it was that you learned it. For every action, there's an equal and opposite reaction. I told you guys yesterday, I don't like stating it that way. I don't like stating it that way because I think it leads to a misconception. Okay, if I have two cars colliding like this, and I focus on one car, then what we tend to think when we repeat and think of Newton's third law in that way, we tend to think that the force acting on A, which is to the left, will be equal and opposite to the force acting on B, and we start labeling them like this. Then we start saying, well, okay, F net is equal to the sum of the forces, FA plus FB. But the problem with that is that those two forces, FA and FB, although they are equal and opposite, I've got them drawn wrong. They don't act on the same object. They act on two different objects. FB is the equal and opposite reaction force, but it's the equal and opposite reaction force acting on the second object. Okay, we're going to forget that. If we say for every action there's an equal and opposite reaction, we forget that it's acting on a different object. And it's a big deal, because if I look at it this way, the way that I had it drawn first, the net force would always be 0. And an object at rest would always remain at rest. And an object in motion would always stay in motion at a constant speed, because there would never be a net force. Of course, we know that can't be the case. There can be a net force. And we can see that there's a net force on object A here. It's caused by the action force. There's also a net force caused on object B, which is the reaction force, FB. So we have a net force on both of these guys. Okay, to remember that, the way that I like to state it, same way as we stated it yesterday, if object A applies a force on B, object B applies the equal and opposite force on object A. Okay, mention those, like, very clearly mention object A and object B. Okay, be very concerted about that. Be very deliberate about mentioning object A and object B, because that way we're not going to forget and just make the net force equal to 0. Now, yesterday we also talked about throwing a rock at a window or putting a hand through a window. If I threw a rock at this window and it bounced off, does that mean the window applies an equal and opposite force? Rock pushes on the window, window pushes back on the rock. Same force, but opposite direction? Yeah, of course. What if the rock broke the window? Does it still apply? Absolutely. There are no exceptions to which Newton's third law doesn't apply. None. If object A applies a force on B, B will always apply an equal and opposite force on A. If the rock applies a force of 50 newtons on the window, then the window, whether it breaks or not, will apply a force of 50 newtons back on the rock. Now, if, let's say the breaking force, the breaking strength of the window was 60 newtons. Okay, we'll call it F breaking. It's 60 newtons. And I throw a rock at the window, and it hits the window with a force of 40. The window will push back with a force of 40. If I throw a rock at the window, and it pushes on the window with a force of 60, then what's going to happen to the window? It's going to push back with 60 and then break. Let's say I throw the rock even harder than I did when it pushed on the window with 60. What's going to happen? It broke at 60 newtons. I throw it harder, what's going to happen? Well, the biggest force that I can apply on that window is what? 60. It doesn't matter how hard I throw that rock, the biggest force that's going to act on that window is 60. Because what happened when I exceeded 60? The window broke. Can't apply a bigger force when the window's broken. So even though the window breaks, the biggest force that I can apply is 60. Therefore, the window will always apply that force back of 60 if that's what the rock is applying to it. So even if the window breaks, even if I throw it harder, then absolutely, object A applies a force on B, B will always apply a force on A. I think we ended class yesterday with the example of the bug hitting the windshield. Was that the one? Bug hits the windshield. Little tiny little bug goes squish when it hits your windshield, right? Does the bug apply a force on the windshield? Yes. Does the windshield apply a force back on the bug? Yes. Are they equal and opposite? Yes. So why does the bug get squished and the window doesn't? Same force. Bug gets squished because the bug is weak. It's a weak bug. Okay, it needs to be stronger, like the windshield. The force that the bug applies on the windshield isn't all that great because it gets squished. But the force on the windshield applies on the bug isn't all that great either. It's the same force. It's just enough to squish the bug. That's all. Let's have a look at a quick mathematical example here. How can we apply mathematics to this whole thing with Newton's third law? This question says Mr. Dickie's mass is 70 kilograms. Jen, no, I'm not going to ask. Jen, what's your mass, roughly? Let's say 50 kilograms? All right, we'll say it's 50. Okay, Jen's mass is 50 kilograms. Okay, might not be 50 kilograms, probably about that. Jen pushes Mr. Dickie, causing him to accelerate at 2.5 meters per second. What's Jen's acceleration going to be? Let's make a prediction first before we solve this. Okay, what do we think Jen's acceleration is going to be? Is it going to be less than mine or more than mine? What's the force? If Jen pushes on me and causes me to accelerate, well, then I'm pushing on her, causing her to accelerate as well, with the same force. But that doesn't mean it's going to be the same acceleration, because she's lighter. How do the accelerations compare? Jen, what do you think?
My acceleration would probably be more than that.
Yeah, it is. We know it's going to be more because your mass is less. Here's how we figure out what your acceleration would be. We would say the force of object 1 on object 2 is equal and opposite to the other force. The force on me is equal and opposite to the force on Jen. Now, F is also equal to m times a. We're going to say M1A1 is equal to negative M2A2, right? Force is equal to force, but opposite direction, hence the negative. My mass, 70 times my acceleration of 2.5 equals Jen's mass, 50 times Jen's acceleration, which we're trying to find here. 70 times 2.5 gives me 140, 175. $175 divided by 50 would be 3.5, but it's negative. Okay, 2 questions. Should Jen's acceleration be negative? Should it be? Mine was positive, hers will be negative, because she applied a force on me in the positive direction, then I applied an equal and opposite force on her in the negative direction. So our acceleration is going to be negative. Should it be 3.5? Does that seem reasonable? Yeah, she's quite a bit lighter than I am, so her acceleration is going to be quite a bit more than my acceleration. Does that make sense? It's really as hard as it gets with this type of question.